In this video, I want to discuss and introduce rational functions, talk about how to reduce them, talk about inverses with regards to rational functions. Okay, so what is a rational function? Well, compare them to a polynomial function. One of the big criteria of polynomials was that you couldn't have a variable in the denominator. You couldn't divide by a variable. You can have a coefficient that's a fraction. You can have numbers in the denominator, but you can't have variables in the denominator. Once you do, you're not a polynomial anymore. Then you are what's called a rational expression or rational function. Okay, so a couple of examples of rational functions. There's one. You can have multiple variables, doesn't have to just be one. There's another rational function. Okay. Okay, so there you have it. There's a couple of rational expressions. Okay. Now, when we had polynomials, there's really no reason that you couldn't plug in any x value for a polynomial function to evaluate the function for that x value. All right. So the way to say that using the language of domains and ranges is we say that the domain of a polynomial is all real numbers. All right. There's no limit. Okay. However, rational functions are not the same. There are limits to what you can the argument values that you can have. Okay, why is there a limit unlike for polynomials? Okay, well, suppose I had this function. Okay, now if I asked you what f of 1 is, well, that's no problem. That's 2. If I asked you f of 2, that's no problem. All right. However, try to tell me what f of 0 is. What is f of 0? Okay, if you go ahead and plug that in, you'll see that you get division by 0, which is not allowed. Okay, so the domain, in this example, the domain does not include 0. Okay, you'll see this a lot with rational functions where you have a limited domain. Okay, now the domain isn't always just limited to 0. All right, watch this. G of x is equal to x squared over 7 minus x. Okay, now you can plug in 0 just fine. 0 gives 0. Okay, 1 and several other numbers are just fine. Okay, so what do you think is the problem here? Well, remember, the problem is not 0 itself. The problem is having a denominator of 0. Okay, can you think of a number that would give a denominator of 0? Okay, well, that means that 7 minus x would have to be 0. What about g of 7? That's going to give the division by 0. See that? So the domain can be limited to in different ways. Okay, the goal, of course, is to avoid dividing by 0. Now, the domain can be limited by more than one point. Let me give you another rational function. What if I had h of x is equal to x over x plus 1, x minus 2, x plus 3? Okay, so can you see that there's multiple values that are going to make h be undefined? Okay, for this one, we would say that domain is all x does not equal minus 1, and x does not equal 2, and x does not equal minus 3. Okay, so there's 3 points we have to avoid. Now, you can often simplify rational functions, rational expressions in a similar sense to how you reduced fractions when you just had numbers. Remember when we had 2/4 and we reduced it to 1/2, or 2/10 and we reduced it to 1/5? All right, let's ask ourselves what exactly was going on when we did reduction. Okay, well, we know that we're allowed to multiply anything by 1 and it won't change the value. For both of these, I could multiply by 0.5 over 0.5, right? That's equal to 1. Anything divided by itself is 1, except for 0 over 0. We won't consider that. So if you multiply all of these fractions by 0.5 over 0.5, that'll give you the reduced versions. Okay. Here you want to multiply by 1/3 over 1/3 to get 3/4, but that's the idea. All right. Another way to understand it is the following. Let's do the 9 over 12. You can think of that as 3 times 3 divided by 3 times 4. And when you have it factored, you can cross out the common factors because those are just going to make a 1, which is unnecessary. Okay, let me show you now how this works with variables. Suppose that we had x plus 1 times x plus 2 divided by x plus 2 times x plus 3. Okay, likewise, just like I showed you before where I had the factored form and I crossed out the terms because I just made a 1. Anything over itself is 1. So that over itself, that's just going to be an unnecessary multiplication by 1. So I can get rid of those, and then the reduced form will be this. Okay? But notice you have to factor first. Okay? If you don't factor, you're not allowed to cross things out. The same thing was true with numbers. You got bit if you try to cross things out when you had an addition instead of a factored form. Like, for example, 3 plus 1 over 3 plus 2. That's 4/5, right? However, if you foolishly do this, if you say, oh, look, I have 3's in common, so I'll just cross those out, and so what do I have left? 1/2. Okay, that's not going to work. Okay, you can only cross things out when you've got multiplication. All right. Let me give you a little more difficult example of one to reduce. So how about this one? Okay, so how would we reduce that? You can't cross anything out because it's not factored. So first we have to factor it. The first one factors to that. The second one factors to this. Let's see. Actually, I need to fix the bottom one. The bottom one, you know what? Let me redo the bottom. The point is you're going to have to factor both of them. So now factoring would give us x. No, that's not going to work either. Oh, x plus 2. There we go. Now I got it. Okay, if you had this red expression, then factoring it, the bottom would give x plus 2, x plus 1. Okay, and so now you can see the point that I was badly trying to make. Now you can factor. Okay, but notice it took a little more work for this one. You didn't start with them in factored form. Okay. All right. Now, regarding inverses, you can find inverses by swapping the x and the y, and then solving for y again. All right. Now, you're going to reach a situation often where you have to have a limited domain. okay, because not every rational function is invertible. Let me finish by talking about two of our basic rational functions. So let's do the inverse of 1 over x and 1 over x squared. Let's first start with a quick sketch of what each of these looks like. One over x looks like this. 1 over x squared looks like that. Okay. Now, the graph of y equals 1 over x, the function 1 over x, that has an inverse of 1 over x. So the inverse is also 1 over x. So the inverse is the same as the original function. Okay? The domain of both of them, both the original function and the inverse, is everything except 0. All right? Now, for the 1 over x squared, for that one, that does not have an inverse. However, we can get an inverse for a limited domain. All right? If we only considered the positive part, let's try to solve for the inverse. Okay? So I'm going to swap the x and the y, and now I'm going to solve for the y. xy squared equals 1. Y squared equals 1 over x. Y equals plus or minus 1 over the square root of x. So I said that it's limited, so we're going to limit it to only considering the positive part, 1 over root x. Okay, so that is the inverse of 1 over x squared, and that's only for a limited domain. Okay,